Okay, I think you can pretty much hear. Okay, so it's recording now. So this is the thermal camera. I'll just explain it, what it is and what it looks like. So here's the front. These are some settings on the top, which you...
Excuse me, is it going to bother you if I open this a little bit right now, or can we come back a little later?
Can you come back a little later?
How long? About an hour?
Yeah, an hour. Yeah, that'd be great. Thank you. So there are different buttons on here. You can sort of figure things out for focusing and whatnot, but we'll deal with all of that. We'll just start from looking at the back of it. I don't know if you can see that well here. But in the back there's this green thing. You'll be able to see there's this green thing, and these sort of allow you to find a single temperature and sort of output that as a voltage value. So that's what we were sort of using to monitor voltage to monitor the temperature at one point on the sample. I mean automatically, because there's no real good software to interface this with LabVIEW directly, so we sort of have to output a voltage. You have to change some settings. So here's a BNC cable, and believe it or not, BNC is also like a video channel. So you can hook this BNC cable to this TV, change the monitor to the right channel, and you can actually see what we're going to see on the screen. But if you use the computer, you can also do the exact same thing you can do from the monitor, from the TV screen, except that you can make some different measurements as well. And then there's this Firewire cable, which is going in here. Firewire is a analog signal. Therefore, there's no such thing as a Firewire to USB connector, because USB is digital and Firewire is analog, so that will never work. Therefore, they have to use this card, and this is computer. And here's the power switch. The thing about this is there's no off switch. You just pull the plug to turn it on. There's no off, which is sort of funny. I know it's calibrated actually in 2013, so sort of recent, relatively. Okay. So now we'll go to the front side, and we'll be doing everything from the computer, since I guess you can see it a little easier. Okay. So if you couldn't already tell that this right here is a transducer. And it may look like this all different temperatures right now, which is not true, because based on the reflection of light, based on if I get closer to it or not, I can sort of change the temperature, because the infrared radiation is coming off of me. It's hitting the transducer, and then it's going to the thermal camera. So you have to know something called the emissivity of the sample in order to measure the properties accurately. So sort of based on the color of the sample, if it's shiny or if it's dark, it will read different temperature values. But we'll get into that later. So this is a transducer. The way I got here on the program, the same program is on that computer as well. There's also a Firewire port in the back, but I found this easier just because it's right here. It's sort of just maybe easier to use a different computer than for your samples and have everything going to one, have the cables jumping across the lab here. So here, if you look at the screen, there's something called FLIR IR Camera Player. So there's two types of programs to control this thermal camera and get the image. There's one is like a more complex program, and one is the more simple program, similar to using the TV screen, and the controls directly on the camera itself. So this is that similar approach. So if you just double click that and you press OK, it'll give us some different options. One of the options is how many images do you want per second, and there's like a little thing right here. It says 60 hertz. And 60 hertz is too fast, at least for this computer, so I have to actually change that to 30 hertz in order to get an image. And this is a black and white thermal image. Really what the thermal camera is doing is measuring temperature using the piezoelectric elements, and it's converting that to a color. So the thermal camera doesn't actually see color. You are just, it's just converting that to color so you can actually see. One of the things that's really good about thermal images is that it's really easy to interpret. So if you want maybe to include in your heat generation or losses pictures, you know, we put a picture like this, and people they really easily understand. If they don't understand anything you're saying, they'll see a transducer with red in the middle. They'll think that this is hot, losses are a problem. Let's do some research on it. So this is that. There are other things that we need to do. So first thing, maybe we'll just talk about a basic control. And we can do that from here, or you can do that from there. Let me get some small electric. Let me just change this with this. here, and I'm just going to basically use this to show you how to focus the thermal camera. There's two buttons up here. This is A, F, and S. That's A is autofocus, F is focusing far, I think S is focusing. What does it say? There's like a little drop box here. X is, oh sorry, that's not it. This is autofocus, A is auto, F is freeze. Oh yeah, there's this little like arrow button. There's this little target. It says autofocus, no. Focus near, and then there's one focus autofocus, and the other one is focus far. So basically we can press these buttons. See, this is getting more blurry. I'm focusing far, so we have to focus closer. So we have to focus near. So it's the flower button. I don't understand who created it. So this focus like that. One of the easiest ways to focus is either that you heat up your sample and then you try to adjust your thermal camera, or you can maybe use something very shiny, because things that are shiny are really easy to detect. So right now the temperature that we're measuring is not the actual temperature of the sample of the material. It's sort of we sort of have to put that emissivity value in. But basically, what I actually end up doing to focus, because there's also another lens which I'm going to show you for the thermal camera. And that'll allow you to get closer and get better resolution. But if you want to get the best possible resolution with this setting right now, what you should do is you should focus near completely. So you hold that button down. And if you were using it on here, there'd be this button over here. See, this is focus far, this is focus near. So you can do the same controls as you would there. And then basically what I do is you sort of just approach it. Okay, now it's getting more blurry. So you can see the needles. When you have a more specific like piezoelectric element or something like this, it's a little bit more easier to focus here. Maybe this will be easier to focus. So you can see all the B and C connectors and whatnot. So right now we can sort of get a good idea. If you go, this is too close. This is what you get you bad measurements. You'll be able to tell sort of by zooming into a different, and we'll be doing it more. But realize if you go like this, you're not going to get a more accurate measurement. Things will get blurry because the camera will get out of focus. So you can't make infinite resolution measurements. For this measurement itself, each pixel, I calculated a while ago, each pixel at the closest focus distance, which is probably about this size, this distance right here I'm showing you, it's about 1.2 millimeters. So if your sample is 1 millimeter, you can't measure the temperature accurately on the side of the sample. Now you can measure on the top of the sample, and I'll explain what that means. How do you do that? So I did a lot of research sort of how to use this. Not research, but like I used it for an experiment, so I had to sort of know and figure out what to do and how to measure. So I was talking about, so it was 1.4 millimeters, and they say that if 1.2 millimeters is 1 pixel, then to make sure you at least have one entire pixel on your sample has to be 3 times as big. So there should be 1 pixel above, 1 pixel on, 1 pixel below, because your sample will either be between them. You can't get it exact, perfect. It's impossible. It's pretty much impossible. So your sample has to be smaller than like about 3.6 millimeters approximately to be able to measure it accurately. 2 millimeters, you can sort of adjust it properly, and you can maybe get 2 or 2.5 millimeters. But any closer than that, you're not going to be able to measure it. You have to try. You have to either use a different lens, or you can actually it will allow you to focus while getting closer, which will show you that lens, so allow you to get closer. But for this sample, for this thermal camera, that's the limitation. So as I just mentioned, here's the is there any settings I can change here? So you can also record. There's a start capture button, so you can sort of record something heating up during this using this. These are options here. Settings, settings. No, I think you can't really change too much here. But for example, now I'll go into the settings on here. There's different arrow buttons. You click one of these arrow buttons. This sort of zooms in. This allows you to zoom in, but this is digital zoom. This is not optical zoom here. I think it's more clear if I just use this. This is optical zoom. It's not. The digital zoom, not optical. So you're not going to get any more accurate. But you can sort of adjust this a little better if you want to adjust, or you want to make it clear what you're measuring. You can sort of get closer or farther. See, now it's getting more blurry. Now it's getting more sharp. that's just one way to do it here. But we'll look at the whole sample. Is this too close? There you go. That's the whole thing. So I was going to talk about the menus on this camera itself. So let's start operating backward. I'm used to it a little bit. So here's analysis. You can, for example, you can add a spot measurement. You can add a box, so you can select a box. You can draw a box shape, and you can start the measurement like that. You can add a differential measurement, and this is a really important tool to use, differential measurement, because sometimes the thermal camera sort of drifts in temperature a little bit, or the temperature of the surroundings changes. So if you're measuring temperature over a long period of time, you may start with 15 degrees room temperature, and then afternoon, you know, in this building, afternoon it could be 20 degrees in the same room. So you sort of don't know your difference. So in this sort of corner, I think you can see it a little bit. This is 1 minus R. So there is a reference. There's a reference measurement going on somewhere. I don't know where the 1, 2 is right now. I think it's because I'm in the menu. It's not showing it. But it's sort of, you sort of want to use a stable temperature. Maybe something on your sample holder. That's sort of why I put that white mark on the top, because I'll explain it later. But it's better to use a differential temperature for a temperature that's going to be constant on your screen. Maybe something like the sample holder or something on your sample itself, which is going to heat up, so you can tell the relative change in temperature. Going down the list here, I don't know what that is. Alarms, that's not something you need. Range. Range will tell you what range you're using. You're probably going to use this range. You're not going to use 500 degrees. You're going to use this one, -40 to 120. You should not have to use over 100 ever. So we'll keep going down. Settings. If you go into settings, you can go. Yes is to go. You'll figure out how to use it, I'm sure. Then you can go to. There's something called analog ports. That's something we need here. I think we can go back in our settings and go up. Camera output. This is what I was sort of talking about. Here we enable the analog channels, which are the channels in the back, which output is 0 to 5 volts for the temperature range you specifically set for a certain spot. So right now, spot number 1 is coming out at analog 1. If I set the minimum temperature for 0 and the maximum for 100, it'll output 5 volts at 100 degrees, and it'll put 0 volts at 0 degrees. So depending on your sample, you may want to change its. You may want to change that range. If you're expecting maybe a 20, the sample will change. Either it'll be less than 100 and more than 15. You could adjust your sample in that way. And the 4th channel in the program actually measures the DC voltage. So that can actually be used. That's sort of the multi-purpose channel, the 4th channel on the continuous drive. That can be used to measure temperature. I think it's digital 1 just go on. Okay, it's off. So enter. So let's go in that. There's another where I forget. I can't remember where the one is for. Is it camera output, and there's one for setting those parameters here. Is it analog ports? Yeah, analog ports. I was mistaken here. So here's something called analog ports. So here's what I'm talking about here. The low value for channel 1 is 20 degrees, and the high value is 100. So if it's lower than 20, it's going to output 0 volts approximately, and if it's around 100, it's going to put out 5 volts. Because sort of there's noise, and on the oscilloscope you're measuring maybe 20 kilohertz signal, 100 kilohertz signal, or 40. There's a lot of sort of ripples and noise going on in the voltage signal. So what we do, you put a capacitor on the back, and the capacitor pretty much grounds any alternating signal and sort of smooth. They call it a smoothing capacitor. So it'll smooth out your data, and you'll be able to get a reasonable value for the voltage. And then, as a researcher, you know what voltage value means what temperature, and you'll convert that later. But perhaps a good way to know the temperature is just to look at the diagram, because that has some air and fluctuation, and if you look at the thermal camera sort of output here, you can just write down the temperature by hand if you want to do that. Okay, so that's these things. So now what we would like to do is go into the other program, which actually,
What are these?
these are spot temperatures. So this is a temperature here and a temperature here.
How can we change these plots?
Okay, so basically you go here, analysis, edit. You can add another one, or you can edit this one. So just edit. And you go up, but you when you use the actual program, you won't need to be doing this.
What is 1 minus R?
The 1 minus the reference temperature. I remember I told you. Let's say this: if the room drifts in temperature, you want to have a stable reference temperature to be able to tell if your sample really increased 15 degrees or increased 3 degrees, because the room increased 15 degrees, or the room increased 12 degrees. So you can understand drift in temperature. Sometimes the thermal camera makes like a shutter sound, and that sort of change. I don't know exactly what is happening when it does that. But it makes like a clicking sound, and all like the colors sort of readjust, and this readjustment sort of causes apparent temperature change. So by having a reference, you sort of save yourself from disabling that shutter phenomenon, or by accidentally forgetting about it and it happening, and you're not able to account for it.
You put the reference separately?
Yeah. So basically, reference. So I can set this as reference temperature, for example. I can set 1 as reference temperature, and therefore it's 0, because 1 is the reference temperature, and the reference temperature is 1. Although it's showing 0.3, which is not making too much sense. But so I think if you go here and we maybe remove all would be the best option. So nothing's there. Then you add a spot. You can add a box in the same way you just draw a box. Add a spot here. So add a spot there. So let's say that's a sample. And then I have reference temperature. This is a little black, so I'll just put that right there. So you can sort of see it, but you can't. It's right there. So then if I want to add a reference temperature, I'll add another spot. It's funny how I can do this backward. I think I used it a lot at one point. So this is that. So that's the good exit. So we have 2 temperatures here. They should be about the same temperature, but they're not. They're 1 degree's difference, probably because the emissivity of the 2 things are different. So now we want to add a difference temperature. So difference of 1, and then the other one should be not reference temperature, but spot. And we want to add number 2. 1 minus 2. So this reference temperature is a good starting point. This is -1. Okay, whatever. A -1. But then when the sample increases 10 degrees, this will stay the same technically. So therefore you'll get 9 degrees. So you'll see a temperature change of 9. So with the thermal camera, it's not so good to present absolute values of temperature. It's more useful much more accurate for difference in temperature values. So here I just showed you, and you can take videos of the you can take videos of the thermal camera, although this is not really a good computer for that, but you can, and you can also take pictures. So if you want this for your presentation, it looks really nice. It's very colorful. People understand. You say loss and you show a transducer with heat, and it looks bad. It looks like something you don't want. So therefore, okay, so I just stopped everything. This is a play button. This is a stop button. Now we'll get into the thermal camera software. It's called ThermalCam Research. I can send you this program, and we have the license for it. So it's sort of I have it as a download, but you can't download this program on the internet. So if you lose that file, you don't have it anymore. So right now you open the program. There's nothing there. You have to go into a thing called camera. Is this showing everything? It's not showing the thermal camera, the transducer that well. I'll just look at this again if you forgot what it looks like. So I go into show camera image. It's already connected, and it'll do this. So now it's showing the camera image. We can have a thermal camera picture of everyone by the time we leave today. If you're interested, I'm putting something like that on Facebook or something. Okay, I don't know. Okay, so why is it all black? I guess it's not working. We're done. So this is like this candle image because this program allows you to define a lot of parameters. So I just press this candle button to sort of readjust the temperature by itself. So look now, before it was like red and green, now it's yellow and purple. That's just because the color you choose. It's arbitrary. Whatever colors you want to use, you can use. See that little thing right there? That's a little nut. There. Is that a little nut? What is that? Yeah, that's a little nut there. So that's kind of. So basically the lighter spots are a reflection of light, and the darker spots are so emissivity, which due to a material's ability to reflect and emit light as something which has a higher temperature than the surroundings, it will have a different emissivity, which means the color you have to adjust the emissivity to get the right temperature. So when we do this experiment, we will not be able to measure the temperature on the metal part. Although when you show it in your presentation, you will show it as one image because it has one emissivity. More complicated programs can say that, hey, I want one emissivity here, I want one here, I want one here. Then the program will be able to do that for you, and you'll get all the temperature correctly. Otherwise, you should just focus on that one part, and maybe this will just be good for general evaluation. So right now, I'll show you how you should make the temperature measurements. Let's say this is the distance we want. This is about, I think the true, tell me if it's getting better, worse, better. It's not a very scientific way, but I think it's the best way to come up with the important distance, the relative distance. So as I think, first you have to measure the temperature of the room. The way you measure the temperature of the room, which is called the reflected temperature, is you put something shiny in front, like this foil thing I made. You can find this procedure online too. It's very standard. So you put this type of shiny foil. Maybe I'll adjust it so it gets a little bit more. That's about as good as it's gonna get. So because wherever you place your sample, there's gonna be light coming. All these different things are creating heat and stuff like that. So you want to measure the sort of reference base temperature that you want to know, because the temperature that the thermal camera is seeing is partially the reflected temperature that other things around it are emitting light because they have some temperature and they're hitting the sample and it's bouncing back, and part of it is the sample's temperature emission itself that it's doing. So to sort of find the combination of that, for example, the highest emissivity that we can usually find is 0.95. That means 5% of the temperature that we're measuring is from the outside surroundings, and 95% of it is from the samples. So if you can figure out what temperature is of the outside surroundings, we can figure out what temperature the sample has by the temperature that the thermal camera makes. But if you integrate that temperature already in the program, and you integrate the emissivity already in the program, you won't have that problem. It'll tell you the real temperature, and it'll do those corrections for you. So basically what you do here is first you go to image settings, scale, object parameters. I believe you set it for 0.15. You'll have to correct me if I'm wrong sometime. 0.15, and you press OK. And then you draw a box here. I drew a box. I click this box button, I drew a box, and I go in results. Now here's the temperature. It seems to be changing kind of fast. Let me just change it. It's 30 Hertz, so that's good. So the temperature of AR01, which is the box that it showed, the average temperature is, this is negative 43. That's not right. There's something up here. That should not show negative 43. Well, it could. That's sort of strange. Okay, so let's try it again. 0.95. Let's go back to the original one setting. So this should not show negative 43. Maybe I'll stop it and try to see go online and see what I should actually be setting, because that can't be right. Reflected temperature 0.15. Okay. Okay, this is that. I may be making mistakes somewhere here, but I don't think so. This is the average temperature in this box. Let me make a spot here. Yeah, saying that. Let me just stop this 1 second. How did you find that this is 0.15 and then can you look at your phone? I did this before, but this shouldn't come up like this. It shouldn't come up as negative something. Oh no, I forgot. Oh, calculate limits, fixed limits. Yeah, you set the how to determine reflected temperature? I believe it. You put 0.1. That's what I remember. You put the. You changed it. Oh, I changed the emissivity. Yeah, you changed the emissivity to 0.15. Therefore, that's the approximate emissivity of the. Is it doing it for everything? Oh no, it's 28.1. Usually it would be like 25 degrees or something, 20 degrees. We can plug in our. But if you're using a reference value which is relatively close to your sample temperature, then it's not a problem. I mean, close to the room temperature, like you can just use this for now. I'll just move it from here. What?
Shows that we have to set the emissivity at 1.
1? Oh, okay, that's the problem. It's not 0.15, it's 1. Okay, that makes sense to me. Okay, emissivity to 1. That's my fault. Okay, let's start it again. Okay, no recording. Okay, so we set the emissivity to 1, and you press OK. Now we get a good temperature. Now it's the temperature average is 17.0, so we're gonna go back here. Settings. We'll put 0.95 again. And the reflected temperature, you have a thing here that says 17.1 degrees. That's the temperature of the room. Bad value. Oh, I said I put a comma. 0.095. If you ever get a newer thermal camera, it'll come with newer software. This is the old software, but it works decently. So we have this measurement now. See, now one thing I had to do, because there's no real, it's hard to get a standard value of the emissivity. How do you measure the emissivity of your sample? So basically this is like Scotch Super 88 tape. I'll show it here. And basically I found one reference. The only reference I could find for a standard material where they actually reported the emissivity value was the Scotch 88 tape, and it has the emissivity of 0.95. And I found on a website that whiteout actually has the same emissivity. But in order to prove that, basically what I did is I put a piece of tape across here, and I covered part of it with whiteout. I heated the whole thing up, and I found that the color of the whiteout was exactly the same as the color of the tape. I couldn't distinguish the two. And because I couldn't distinguish the two, they're the same emissivity. So I sort of experimentally found out that you can use whiteout to cover your sample if you put part of it on your sample. So if you want to be like sort of more technical about it, because I didn't do that with PZT necessarily, because PZT is really small, so it's sort of hard to get that accurately. So I'm just going to put it here because it's not going to dry so fast. It's not conductive. Damaging the sample. It's not the best thing because it sort of peels off, but If you want to use a different, it's nice because it can be taken off. Whiteout is not that tough. You can take whiteout off. So actually, we're going to be seeing today. See, look, it looks a little darker, doesn't it, in the middle? So because it looks a little darker, you can actually know, you'll actually realize that that ceramic has emissivity lower than that whiteout and Super 88 tape, which is maybe like 0.95 or something. You can calculate it yourself, but because and this actually transducer has some coating on it on the PCT to protect it, so therefore it's gonna change. It's gonna be more reflective. Like if something's really shiny, generally it has a lower emissivity. Generally, so okay. So now we did that. Now we can take the big picture of our sample. I think I can delete this box here. I think you have to left click it and delete. Okay, so now what we want to do, we have the right emissivity, we have the right sample. Now we're going to have to hook it up to the voltage. So, what's the resonance frequency? I'll just measure the current too. Okay, so here's the output, output. Let me just hook it up here, just show what I'm doing. So normally how you would hook this up is the middle plate would be the positive voltage, and the lower plate, because the lower